So I'm going to talk about a 28nm processor that has features that allows it to operate at a lower minimum operating voltage than the intrinsic minimum SRAM operating voltage. And so this was work done during my PhD at UC Berkeley. So the motivation here is that dynamic voltage and frequency scaling is a great way to improve energy efficiency. So as your performance requirements change over time, you can change your voltage to maximize energy efficiency while still meeting all of your performance constraints. Unfortunately, SRAM typically limits the minimum operating voltage of your system. So process variation in modern technologies is already causing a lot of problems. It makes transistors significantly stronger or weaker than intended. In logic, this ends up being okay because there's a lot of margin built in, the variation's uncorrelated. But in SRAM has the smallest transistors, and it has the most transistors on the die. And together, these two effects make it such that large deviations in transistor strength within the SRAM bit cell are actually fairly likely. So as you lower the operating voltage, these weakened bit cells begin to fail. And this is failing not just for retention, for holding onto their state. This is failing to read or failing to write. So the approach we like to take is a little bit different than what's done in the past. So this plot shows the bit cell error rate or failure slope for generic SRAM shown in blue. So the y-axis is the bit error rate, and the x-axis is the voltage. And note that the y-axis is on a log scale. This means for a 50 millivolt reduction in VDD, you get about a 10 times increase in the number of errors you see. So the minimum operating voltage is set by the intersection of this blue line with the horizontal red line, which is the maximum allowable failure rate. And so to move this intersection point lower, to decrease the minimum operating voltage of your system, there are really two ways to go about it. The first one's the most common, and this is preventing errors from ever occurring. So I'll talk about it later, but this is things you do to the SRAM periphery to improve the bit cell's operation at low voltage. But there's also a second way to reduce the minimum operating voltage, and this is to essentially tolerate these bit cell errors, and this shifts the red curve up. And it's important to note that you can actually do both of these at the same time. You can both prevent and tolerate errors for further Vmin. So this talk is going to focus on how to tolerate errors. And I claim that you can get pretty significant Vmin reduction by tolerating on the order of 1,000 bit cell errors per megabyte of SRAM. So there's been a lot of related work at the circuit level. There have been a lot of publications over the last 5 or 6 years at these assist circuits. So they'll go into the SRAM periphery and generate these extra voltages that will either overdrive or underdrive the gate voltages of transistors. And that allows it to overcome the process variation of the devices and lower the minimum operating voltage. There's also cell upsizing, so you can switch from a 6-transistor cell to an 8-transistor cell. This is expensive in terms of area, but you can operate at a lower voltage. At the architecture level, there have been some techniques to tolerate errors, but they aren't really targeted at Vmin reduction. So traditional fused static column redundancy is used for high voltage static faults. And what I'm proposing is something that goes much further than that and repairs 10 to 100 times more errors than regular column redundancy. There's also error correcting codes. These are generally used for soft error protection and haven't really been proposed to reduce Vmin. But error correction is difficult to implement, as I'll show later, because the encoding and decoding process adds a lot of latency. It's also a lot of overhead for small access word sizes. So overall, the goal of this chip is to prove that the SRAM Vmin can be lowered by tolerating a reasonable number of failing bit cells. And the target for this will be a 28nm processor with a 1 megabyte L2 cache. And the overall intuition here is that we'd rather target the tail of the distribution. So this is a cartoon of a hypothetical distribution where these are SRAM bit cells, and if they're in the tail of the distribution, they fail. Assist techniques, such as negative bit line, shift the entire distribution. So for negative bit line, they'll generate a negative voltage on the bit line, and this essentially doubles your write energy every single access. And you don't actually need to double your write energy every access. It's only a couple cells that need this. So ideally, we like to target the exact bit cells in this failure region. And that's the kind of techniques that I'd like to talk about. So RISC-V is a great project to enable a project like this. So when we started looking at these ideas, we quickly realized that just doing kind of whiteboard design of pipeline diagrams or modifying architectural simulators was going to make it really hard to truly believe that we caught all of the implementation issues. And of course, just estimating the overhead of these techniques is also pretty difficult. What we'd really like to do is just implement this at the RTL level. And so luckily, we were able to use the rocket ship generator to generate a baseline processor. And then we went in and modified the caches and added a BIST around the SRAM to implement these techniques that I'm going to talk about next. So these are the 3 techniques I'm going to talk about. The first is dynamic column redundancy. So this is used to protect the majority of the bits on the chip. This protects the data portions of the caches, and it allows the avoidance of a single bit error. However, at low voltage, the probability that you have a 2 or 3 bit error is actually much higher than an overwhelming number of single bit errors. So the second technique we have is line disable, to essentially disable ways in a set associative cache that have 2 or more bit errors inside them. And the first 2 techniques protect the data portions of the arrays. There's also tag portions that need to be protected. So the last technique uses standard cells to essentially bypass the failing cells inside tag or other arrays, such as like a branch predictor. This is the system architecture. We have 3 voltage domains. The first voltage domain is the core, which has the rocket pipeline and L1 cache. The second voltage domain has the 1 megabyte L2 cache. And the third voltage domain is the uncore, which communicates off chip through the host target interface. Both the L1 and L2 cache have the 3 techniques I talked about, line disable, bit bypass, and dynamic column redundancy added to them. There's also an on-chip built-in self-test that identifies all of the error locations in the SRAM so that we can avoid them. Last, we have ECC on all of the SRAM as well to make sure that we can catch errors as they come out and ensure that we didn't actually miss a bit error when we did our programming. We don't actually use the correction capability of the ECC, we just use it to log errors. This is the general idea behind dynamic column redundancy. So on the left, the figure shows how you would store a 4-bit word. You have 1 extra column, which is your redundant column. And traditionally, fused static redundancy looks exactly like this. There's a bank of 2-to-1 multiplexers that uses a thermometer code to shift out the failing bit. However, this will only shift out 1 bit for all the rows in an array. So in dynamic column redundancy, we actually change the address to this mux on a row-by-row basis. And in this way, we can map out failing bit cells in multiple rows. The other advantage of this is that the number of bits that we cover with this redundancy address is programmable. So we can use 1 redundancy address per row, share 1 between 2 rows, or use a single one among all 4 rows. And this is much better than ECC, which is usually enforced to work on the access size. So if you have a 32-bit access, you really need to do a 32-bit ECC word, which has a lot of overhead. Whereas this, you can kind of tune at design time exactly how many bits you want to be able to correct by determining how many bits each redundancy address covers. The overhead to do this is actually fairly simple. So on the writes, you need to encode the data before you write the data into the array. And then on reads, you need to decode the data to shift out the broken bit. The redundancy address is stored inside the tag arrays. And so it's actually accessed in parallel with the data and doesn't add to the critical path. The only thing that adds to the critical path are these encoding and decoding muxes. Most of this area overhead is actually inside the tag array. Because as you can imagine, these redundancy addresses are log2 of the data word. And so they do actually add up. But because the tag array is an SRAM, you can store those bits fairly densely. This is exactly how we implement the encoding and decoding procedure for DCR. So when you encode it, we basically need to duplicate the failing bit. And we do this with 2-to-1 muxes. And then for decoding, we do the opposite. We shift around the failing bit. And so it's only these muxes that ever appear on the critical path. So that was the first technique. And like I mentioned before, there are still double or triple bit errors that will cause problems. And so what we'd like to do in a set associative cache is just simply disable that way. This is expensive because you lose an entire way, but these errors are actually pretty rare. So when we implement this technique, we limit the decrease in cache capacity to only 1%. And when we do this line disable, we do this during replacement. An LFSR and a priority encoder basically randomly selects the first valid way to replace the data into. Last, DCR and line disable store kind of their reprogrammable redundancy information inside the tags. But the tags themselves could have an error. Instead of requiring that the tag array has assist techniques that are used nowhere else in the design or is upsized with bigger cells, we propose using an expensive but workable bit bypass technique that uses standard cells to create a map of all of the failing bit cells inside the tag array. And what happens is during a write access, the address is compared with this associative array. If there's a row hit, then we look at the column that's broken and peel out the bit we want to write and store it in a redundant flop. And then during a read operation, we again look up in the associative array whether the address is a hit, and then mux in the fixed bit into the output data. And so we can repair up to 2 columns per row with this technique. And you can imagine this is actually quite a lot of standard cells. But because the tags are a small portion of the overall number of bits in the system, you actually don't need to make that many corrections. This is the L1 data cache pipeline with these techniques added. So the reprogrammable redundancy is shown in red, and it's actually pretty simple to add. You just add these 2-to-1 muxes before and after the data SRAM. You add the redundancy addresses into the tag. You have bit bypass to protect the tag array, and then you also check the disable bit during way comparison. What's really nasty is adding ECC. So we needed to add ECC detection in order to make sure we didn't miss anything. We still added ECC correction capability, mainly as an experiment to see just how difficult it would be. In this implementation, we pipelined the ECC decoding so that it doesn't have too much of an impact on the critical path. Unfortunately, this means that the corrected data is available an entire cycle later. Therefore, we ship out the uncorrected data first, and then kind of kill it later on if we detect an error, and recycle the corrected data into the existing cache pipeline. The L2 implementation is much easier. For the L2, you just simply pipeline an extra stage for the ECC because you care less about area overhead. ECC logging is done in parallel for every single SRAM access and is buffered up into local queues, and then an arbiter basically pulls off the error logs over the host target interface whenever errors are detected. And again, this isn't necessary for Vmin reduction. This is just for debugging purposes. What is necessary is the built-in self-test. There are industry programs that will insert built-in self-test into your chip. We wrote our own. We had an existing BIST and Verilog that we used. And in this BIST, we test all of the data arrays and tag arrays in parallel. You'll notice that there's a latch on the output of all the arrays. This is to relax the timing constraints on the BIST controller because the SRAM reads are now forced to happen within half a cycle. And we detect any errors, and then again, use HTIF to pull all those errors off chip. This table compares this technique to some of the other proposed techniques used that tolerate errors. And so you'll notice that the maximum bit error rate, which is equivalent to the minimum operating voltage, is about 1 million times higher than what you can get in the nominal case. This protects both the tag and the data portion and does it with about 2% total area overhead, and that's for the L2. And so if I dive in a little bit more for the L2 area overhead, the data bit is 100, the word length in the data is 128 bits. The extra bits are caused by ECC. This is just for the debugging purposes. And this scheme really is just adding that one extra redundant column. The tag array is 216 bits. We add 1 bit per way for line disable. And then the 13 bits are the redundancy address with its own ECC bits. And then bit bypass is expensive. It adds 15% overhead to the tags. But luckily, the tags only contribute to 6% of the L2 area. So overall, this ends up being about 2% area overhead. if you notice the table, the maximum bit error rate was about 1 e to the -4, and that wasn't accidental. Like I mentioned before, we can tune the number of bits that the redundancy address covers to tolerate different amounts of errors. This plot shows the probability of bit cell failure on the x-axis versus the probability that a word has a failing bit inside it in the y-axis. So at high voltages, which corresponds to low probabilities of failure, none of the words have any errors. And then, of course, because the probability of bit cell failure is exponential, as you get to higher and higher probabilities of bit cell failure, you start seeing lots and lots of errors. Here, in 1 order of magnitude increase in failure rate, you get from 20% of the words having a failing bit to over 80% of the words having a failing bit. And this only corresponds to about a 50 millivolt reduction in VDD. So we kind of targeted something before you fall off this error cliff, where you get most of the voltage reduction while still only having to tolerate a few errors on the chip. In this case, for a 1 megabyte cache, that's tolerating around 1,000 errors. This is the die photo of our prototype. This was taped out in TSMC 28 nanometer HPM. It's 2.7 by 1.8 millimeters and wire bonded. The test setup looks almost exactly like the previous chip. Most of the area is taken up with this 1 megabyte L2 cache, and you can see the core and the L1 in the lower right. For the design flow, TSMC provided the standard cells in the SRAM compiler. We didn't touch any of the SRAMs in this design. We just instantiated them. There are chisel and Verilog wrappers for the BIST, the Rocket, of course, and the L2 was written in chisel. But 2 years ago, we needed to put these Verilog wrappers in to support multi-clock. And then the whole place and route and timing sign-off flow is all Synopsys. This is a measured Shmoo plot of the 28 nanometer chip. On the left, it shows the core and L1 cache. It operates at up to 1 gigahertz, consuming 34 milliwatts. And then down to about 450 millivolts. The L2 cache was signed off at a less strict frequency, so it runs at about 650 megahertz. This is the BIST programming algorithm. So those results before were without reprogrammable redundancy enabled. And now we sweep voltage and frequency and run the SRAM BIST tests. If we find an error in the data portion, we first use DCR, because that's the least expensive way to repair the bit. And then we keep running the BIST tests. If we detect another error, and there's already a redundancy address programmed for that region of bits, we need to disable the way. And then if there's any errors in the tag array, we use bit bypass to fix those. And so this entire thing, all the BIST runs in about 20 milliseconds, which is including 5 different March tests, deep arrays, and after we've programmed all of the reprogrammable redundancy, we send it over HTIF onto the chip and start operation. This plot shows the measured bit error rate of the SRAMs on chip versus voltage for the different types of SRAM. So we use 8-transistor-based bit cells for the L1 cache and high-density 6-transistor-based SRAM cells for the L2 cache. And as I mentioned before, this confirms that the bit error rate increases by about 10x for every 50 millivolts of voltage reduction. And annotated on here, you can see the theoretical Vmin reduction by this technique. And this plot shows the actual measured Vmin reduction for 7 different die. So the pink line is the nominal case, where we decreased the voltage until we saw our first SRAM bit cell fail. Next, we tried just dynamic column redundancy. And this Vmin was limited by the point at which the first double bit error appeared. Next, we turned off DCR and only used line disable, and that corresponds to the orange plot. And in this case, the minimum operating voltage is set by the point at which our cache capacity decreased by 1%. And then the proposed technique is using both DCR and line disable together. And after we turn on both of these, we got about a 25% reduction in VDD for about 2% area overhead. And so we got similar results as well. This is for the L2 cache. We got similar results for the L1 cache. However, because the L1 cache was built with 8T transistors, its nominal Vmin was already a very low voltage. And so these even lower voltages were running at very, very slow frequencies. And they were below kind of the energy optimal point. So to summarize, these proposed reprogrammable redundancy techniques we think are easier to adopt than circuit level assist techniques. to do assist techniques to lower Vmin, you kind of have to be a foundry or a big company that can build a test chip to try out these techniques. And by the time you get that test chip back and test it and figure out exactly how well your techniques worked, all the big design decisions have already been made. But with this technique, you know ahead of time exactly how many errors you can tolerate. And as long as you have bounds on the failure slope, you can predict ahead of time exactly how much Vmin reduction you get for a certain amount of area overhead. And overall, if you look at the raw numbers, this result is showing 100 to 150 millivolts of Vmin reduction, and that's definitely in the range of what assist techniques can offer with even less area overhead. The big drawback of this work is that you either need to do a power-up built-in self-test on every power-up to program these reprogrammable redundancy bits, or you need to do this during manufacturing testing and store all of these bits in some sort of non-volatile memory. But we believe that kind of the huge Vmin reduction you get for low area overhead would make this complexity worth it. So to summarize, I propose DCR, LD, and bit bypass, which are programmed by BIST to tolerate failing bit cells at low voltage. We've shown significant Vmin reduction using just these architecture level techniques without any circuit changes. And if we want even further Vmin reduction, you can certainly use assist techniques as well. And this 28 nanometer processor shows about 25% Vmin reduction, for which we got 50% power reduction and about 2% area overhead. So I'd like to thank all the people who made this work possible, and especially TSMC for the fabrication donation. I'd be happy to answer any questions. Thank you.
Any questions for Brian? We have a question for Brian.
Yes, Dave Ditzel, Esperanto. You said really nice reduction on the level 2 and getting down to about 0.4 volts or so. How did the tag part you implemented with standard flip-flops? What was the kind of the Vmin you got on the standard flip-flops, and how did that compare?
Let's see if I can find a slide. So the tag array itself was implemented using SRAM. So the bit bypass around it was using flops, and at those voltages we didn't see any flop failure.
I guess the question: what's the difference in the Vmin of the flop versus what you're seeing on the SRAM cell with correction? What was the flop Vmin like?
We didn't have enough observability to determine whether it was timing failures or flop retention that failed at the failing voltages.
Anything else? Nope. All right. Thanks, Brian.